and you're ready to go. Have a good session.
Thank you. Okay, so let's wait just like the last few seconds until it starts. Okay, so welcome back to the second part of the session on secret sharing. And the first talk is by Vipul Goyal, Ifan Song, and Akshay Ram Srinivasan. And the title is Traceable Secret Sharing and Application. And Akshay will be giving the talk.
Can you see my screen as well as hear me?
Yes.
Thanks. Thanks a lot for the introduction. And this is based on joint work with Vipul Goyal and Ifan Song. So let me start this talk by describing your scenario. So let's say Alice has some secret data S and she wants to store this secret on the cloud. So think of the secret as the secret key for Alice's cryptocurrency wallet. So to enhance privacy, she chooses n cloud service providers, splits her secret into n shares using a secret sharing scheme, and stores the shares on the service. So there is an adversary who's interested in learning about the secret information that Alice stored on the service. And in fact, the adversary is willing to pay the servers in order to learn this information. So what this adversary does is that it approaches one of the servers, let's say the first server, and promises to pay a certain amount of monetary reward and ask the servers to send the share that it received from Alice and in return for this reward. Even though this offer is enticing, the server is wary of the following possibility. If Alice somehow finds out that it cheated by sending the share it received from Alice to an external party, then Alice could sue the server in the court of law. And if Alice somehow wins this case, then it would not only lead to a big loss of reputation for the server, but it also would mean bankruptcy because of the service agreement that it had with Alice. So how could Alice find out? So for instance, Alice could have some secret information that could be embedded in the share and which would help Alice supposedly win the case. However, the adversary that we are dealing with is very clever, and the adversary comes up with a elaborate cryptographic scheme. So the scheme consists of the following components. So it consists of n functions, f1 to fn, that we call as the collectors function, and it also has a reconstruction box, which we call as rec_star. Now the adversary asks the servers to apply this reconstruction function on their shares and send it to it, and it will then pay the server the promised monetary reward. The adversary further promises the following. So it says that even if Alice gets hold of these collector functions f1 to fn, the collected shares that the servers potentially send to the adversary, as well as the reconstruction box, then Alice has no way of proving that a particular server cheated. So in other words, there is no way for Alice to actually trace a cheating server. So on examining this scheme closely, the server is indeed convinced that this claim is true. That is, there is no way for Alice to prove in the court of law that it indeed cheated. And what would any rational server do? It will send FI on share I and collect the monetary reward from the adversary. And if the adversary is somehow able to convince T of these servers to send the information, then it can potentially learn secret information about Alice's data. So on hearing about this big conspiracy that is brewing, Alice approaches the cryptographic community for help. Specifically, she asked the following question: can we construct a secret sharing scheme that allows her to trace a cheating server as well as provide a valid evidence that could be examined in the court of law implicating a particular server of cheating? And to help Alice with this endeavor, we introduce a new primitive called as traceable secret sharing, or TSS in short. So let me explain the syntax of a traceable secret sharing scheme. So it consists of a sharing phase where we take a secret S and split it into n shares, sh1 to shn. So this sharing phase could be an interactive protocol that is run between the servers and Alice. So the reconstruction is standard. It takes in at least t shares and reconstructs the secret S. And for privacy, we require that any t-1 shares reveal no information about the underlying secret. So in addition to the sharing and reconstruction phase, a traceable secret sharing consists of two additional algorithms, a trace algorithm and a judge algorithm. So what does the trace algorithm do? It takes the view of Alice during the sharing phase. It takes the description of these n collector functions, as well as the collected shares for some subset C of size at least t, the reconstruction box, and it outputs the identity of a cheating party as well as an evidence pi I. And the judge algorithm takes this evidence and pronounces whether the ith party is guilty or not guilty. So what are the properties that we need a traceable secret sharing to satisfy? We need two properties. The first is traceability. It states the following. So for any two secrets S0 and S1, if the reconstruction box on input the collected shares can distinguish between the sharing of S0 and S1 with some non-negligible advantage, then we need the tracing algorithm to output the identity of a traitor along with the valid evidence with some non-negligible probability. So here we require a very weak property from the reconstruction box that it only has to distinguish between two sharings with some non-negligible advantage. And even in this case, we want the tracing to output the identity of a traitor and along with the valid evidence. And the second property we need to satisfy is non-imputability, which protects a honest server from a malicious dealer or Alice in this case. So what does non-imputability say? It says that any malicious Alice cannot provide a valid evidence against an honest server, even if it colludes with every other server. Okay, so we need traceability as well as non-imputability. So what are the main contributions? So we formally define a traceable secret sharing scheme. And unlike the other related notions like traitor tracing and so on, this traceable secret sharing scheme seems non-trivial to construct, even if we ignore the efficiency aspects. So recall that a traitor tracing in a broadcast encryption can be easily constructed if we allow the ciphertext as well as the public keys to grow with the number of users. But here, this is not the case. And our main contribution is the construction of traceable secret sharing, assuming the existence of secure multi-party computation protocol. And we also consider a couple of extensions to this tracing. So the first extension is that for tracing more than one traitor. Recall that if the reconstruction box has to learn some non-trivial information, there are at least t traitors. And the question is, can we trace t traitors? Because there is no hope of tracing more than t traitors because the reconstruction box could just ignore the other collected shares. So here we can do almost optimally, where we can trace up to t-1 traitors. We also consider a setting where we allow collusion between the servers, where servers come together before sending the collected information to the adversary. So recall that if we allow more than t servers to collude, then there is no hope of tracing because the t servers could just reconstruct the secret and send it to the adversary in some encrypted form. So here we allow up to t-1 servers to collude and give a construction that satisfies this collusion resistance. And we also consider an application of traceable secret sharing to traceable delegation of computation. So let's assume that the Alice is not only storing the data on the server, but is also we want to compute some function on the secret shared data. So here we consider a protocol in the offline-online setting where the offline cost of Alice grows with the size of the function that you want to compute, whereas the online cost of Alice is extremely cheap. That is, it goes only with the input and the output length. And we give such a protocol for traceable delegation of computation. So for more details about how we construct such a traceable secret sharing scheme, I encourage you to look into the longer version of the talk, and you can find the full version on it. Thanks.
Thanks, Akshay. Do you have any quick question for Akshay? Okay, if not, we'll go to the next talk. So the next talk is Quadratic Secret-Sharing and Conditional Disclosure of Secrets. And this is by Amos Bemel, Ashton Otsman, and Nati Peter. And Nati Peter is giving the talk.
Thank you for the introduction. Hello, everyone. My name is Nati, and I'm going to talk about quadratic secret sharing and conditional disclosure of secrets, a joint work with Amos Beimer and Hussein Othman. So let's start with the definition of secret sharing scheme, first defined by Shamir and Blakely for the threshold case, and later by Ito, Saito, and Ishizaki for the general case. We have an access structure gamma, which is a collection of subsets of parties. For example, it may have all subsets of parties of size greater than k for some threshold k, or it may have a general structure and contain arbitrary subsets of different sizes. In a secret sharing scheme, we have a dealer that holds a secret S and randomness R, and it uses them to generate n share S1 to Sn, and it sends each share Si to party Pi. We say that a secret sharing scheme realizes an access structure gamma if both correctness and security holds, where for correctness we require that any authorized set which is in the access structure can reconstruct the secret S using its shares. For security, we require that any unauthorized set not in the access structure should not learn any information about the secret given its shares. In our work, we study polynomial secret sharing, which is a broad class of secret sharing scheme, extend the well-known class of linear schemes. In such scheme, the secret is a field element, and the randomness contains random field elements. Recently, Paskid and Radon defined secret sharing with polynomial sharing, in which each share contains field elements such that each element is a polynomial function of the secret and the random elements. In our work, we define secret sharing with polynomial reconstruction, in which each authorized set can apply polynomial function on the elements of its shares and reconstruct the secret. We also define secret sharing scheme with both polynomial sharing and polynomial reconstruction. The motivation for studying polynomial secret sharing is to prove lower bounds on the size of the shares for a broad class of secret sharing schemes, and to develop new techniques for constructing efficient secret sharing with small share size for some or all access structures. Let us recall the well-studied class of linear secret sharing, in which the sharing algorithm of the dealer is done by linear function, which are in fact degree 1 polynomials. So we can view linear secret sharing as a special case of polynomial secret sharing. For linear secret sharing, we know that linear sharing is equivalent to linear reconstruction, but we don't know if this equivalence holds for polynomial secret sharing with degree greater than 1. So linear secret sharing are interesting since many of the known schemes are linear and they have useful properties which makes them good for constructing secure cryptographic protocols. Let's move on to our results. So I start with our lower bounds. Our first result is a lower bound of omega of 2 to the n over d plus 1 on the share size of secret sharing scheme in which the reconstruction is done by degree d polynomials. For comparison, the best known lower bound for general secret sharing is omega of n squared over log n, which is much worse, and the best known lower bound for linear secret sharing is omega of 2 to the n over 2. So our polynomial lower bound somewhat extends the linear lower bound. Our second result is a lower bound of 2 to the omega of n over d for secret sharing scheme with degree d reconstruction, but for an explicit access structure. We know a similar result only for linear secret sharing before our work. In our work, we also study quadratic secret sharing scheme, which are in fact polynomial secret sharing in which both sharing and reconstruction are done by polynomials of degree 2. In our work, we construct such quadratic secret sharing scheme for any arbitrary access structure in which the size of the share is O of 2 to the 0.705n. For comparison, the best known linear upper bound is a bit worse, and the best known general upper bound is slightly better, and such scheme uses more complex tools than polynomials of degree 2. Another result we show in our work is a separation between linear secret sharing and quadratic secret sharing. And you can see the gap between the share sizes of the linear and the quadratic scheme in the slide. Well, I don't have time to go over the secret sharing that we construct, but I will give you a quick roadmap of our construction. So we start with quadratic two-server CDS protocol, which is a simple cryptographic protocol presented by Yuval Kuntanatan and we. We use its ideas to construct quadratic multi-server CDS, and I refer you to the long talk or the paper for more details. Then we use the quadratic multi-server CDS to construct quadratic multi-server robust CDS protocol with amplified security. And finally, we use the transformation from robust CDS to secret sharing developed in a sequence of paper to obtain our quadratic secret sharing. So to conclude this talk, we define polynomial secret sharing schemes, which are a broad class of secret sharing that generalizes the well-known class of linear secret sharing. We prove lower bounds for secret sharing schemes with polynomial reconstruction. We show upper bound for quadratic secret sharing and quadratic CDS, which are better than the best known upper bounds for linear secret sharing and linear CDS. And we show a separation between linear secret sharing and quadratic secret sharing for almost all access structures. An open problem that arises from our work is to prove lower bounds on the share size for polynomial sharing, where in our work we show such lower bound for polynomial reconstruction. And another open problem is to show improved upper bounds for general degree D polynomial secret sharing, where the degree D is greater than 2. That's it. Thank you.
Thank you, Nati. Do we have a question for Nati? Okay. In the meantime, who is presenting the last paper?
I am.
Oh, great.
Mingyuan, yep.
Mingyuan. So, okay, so please share the screen and Mingyuan. So I'm introducing you. So the last paper of this session is a paper by Emant Maji, Anat Paskin-Chernyavsky, Tom Swerd, and Mingyuan Wang. And the paper is titled Constructing Locally Leakage Resilient Linear Secret Sharing Scheme, and Mingyuan is giving the talk.
Okay, yes, thanks for the introduction. So I'm going to talk about constructing locally leakage resilient linear secret sharing schemes. This is joined with Hamata Maji, Anat Paskin-Chernyavsky, and Tom Swerd. So in a classical secret sharing schemes, the security guarantees that any unauthorized set of secret shares is uncorrelated with the secret S. But what if the adversary learns partial information about every secret share? Is the joint distribution of the leakage correlated with the secret or not? So locally leakage resilient secret sharing schemes ensures that the secret is uncorrelated with the secret. So since the introduction of leakage resilient secret sharing schemes, there have been two main research directions. The first line of work tried to construct new secret sharing schemes that are designed to be leakage resilient against very strong leakage attacks. However, these constructions usually incur significant overheads and loses crucial algebraic structures such as linearity. Hence, there's another line of work that investigates the leakage resilience of prominent secret sharing schemes, such as Shamir secret sharing schemes. So our work belongs to this second line of work. So in particular, we consider Macy's secret sharing schemes corresponding to a random linear code. So given any code C, to sample a Macy's secret sharing schemes, one simply samples a random code word conditioned on the first coordinate being equal to the secret S. And note that most prominent secret sharing schemes are Macy's secret sharing schemes. For example, Shamir correspond to Reed-Solomon code, and additive secret sharing correspond to the parity code. So to sample a random linear code, we simply sample the generator matrix uniformly at random. Note that when the underlying field F is sufficiently large, a random code will be MDS with overwhelming probability. And when G is an MDS code, the corresponding secret sharing schemes is simply a threshold secret sharing schemes, where the reconstruction threshold is the dimension of the code, k+1. So our first result is the following. So we'll be using M to denote the number of bits leaked from every secret share. So let N be the number of parties and k+1 be the reconstruction threshold and M be any constant. As long as we have the guarantee that k is greater than half of N, the Macy secret sharing schemes corresponding to a random code will be M-bit local leakage resilient, except with exponentially small failure probability. So to complement this result, we also present a bottleneck for the existing Fourier analytic approach. In particular, Ben Hamoda et al. Introduced this innovative Fourier analytic approach to prove leakage resilience. If you are familiar with the proof, where they use this magnitude of Fourier coefficient as the upper bound for the distinguishing advantage, this approach is adopted by all the existing works, including this one. We show that this approach is bound to fail when k is less than half of N. Therefore, the first result is the optimal result one can hope to achieve using the existing technical approach. So now let me position our works among the relevant prior works. First, in the original work by Ben Hamoda et al., they consider any MDS code G, and they show that G will be leakage resilient as long as k is greater than some fraction of N. And this fraction depends on the number of bits leaked from every secret share. Roughly when M is 1, you roughly need k to be greater than 0.85 times N. In comparison, our construction is a randomized construction. There is an exponentially small failure probability, but we prove a stronger result. In another recent work by Maji et al., they consider Shamir secret sharing with random chosen evaluation places. So they are also a randomized construction. They consider a severely restricted type of leakage, namely the physical bit leakage. But they prove a very strong result that the reconstruction threshold can be as low as 2, and the number of parties can be unbounded. We make a special note about this work because they also employs the existing Fourier analytic approach, and they prove leakage resilience in the setting where the reconstruction threshold is less than half of the parties. However, this does not contradict the bottleneck I just showed you because they only consider physical bit leakage. Now, finally, let me highlight an exciting feature about our proof. So one particular challenging fact is that the number of leakage functions is actually much, much larger than the family of the constructions. Hence, if you consider this standard way to proving the security of randomized constructions, namely, if you fix any leakage function and prove that most code will be secure against this leakage function, then you use a typical union bound over all the possible choices of leakage functions. This approach will not work because there are simply too many leakage functions. So our proof identifies a new set of tests. So every test is specified by a product space. And we say a code word is bad if a large fraction of its coordinates fall inside this subset VI. And the code passes the test if there are few code words that are bad. So to give you some intuition about this test, every leakage function will correspond to some test. Intuitively, every VI will be the set of large Fourier coefficient of Li. And we use a Fourier analytic approach to prove that if a code passes this test V, it will be leakage resilient against this leakage function L. Hence, if a code passes all the tests, it will be leakage resilient. Now, the crucial benefit of defining this set of tests is that the number of tests is actually quite small. Hence, a union bound over the test now become possible. And finally, we employ a combinatorial argument to prove that fix any test, most code will pass this test. So I will not have time to go into more details on the proof, so I will refer you to the long video and the full version for more details. I will end my talk here. Thank you.
Thank you very much, Mingyan, and thanks to all the speakers of this session. And so now it's question time. So I've seen already one question on the Zulip. Rohan Kundu says, it's a question for Akshay. I just wondering, how would the traceable secret sharing scheme behave if we have a quantum adversary?
So I'm assuming that the question refers to the case where the collector or the adversary and the servers have some entangled quantum state, and what happens in that setting. So not too sure. So I would guess that our construction also satisfies this if we instantiate with suitably post-quantum primitives. But yeah, this is something interesting to consider. Yeah, I would conjecture that a construction is secure, but yeah, I'm not too sure.
Thank you. Thank you.
Any other questions?
I have just a follow-up question.
Yes.
Like, if we suppose have a quantum adversary, like, do you have any particular post-quantum primitive in mind for this particular scheme?
So I think what you would be require is a post-quantum multi-party computation in order to compute the shares. So yeah, I'm not too sure. Yeah, whether this is secure if you just instantiate the multi-party computation as a post-quantum. It's interesting to consider settings where the servers and the adversary have entangled quantum state.
Thank you so much, sir.
Okay. Do we have any other questions? Okay, I don't see any other questions. So I guess, okay, we are almost at the end of the session anyway. So let's close this session. Thank you very much for all the speakers. And I think the next